Welcome, class. I hope you're all doing well and staying healthy. So I'm going to talk a little bit today about linear regression. We've started talking about how there are two quantitative variables. We can plot them in a scatter plot and see what sort of relationship they have. We talked about how we try to decide which variable may go on the x and the y axis. So we try to put a variable on the y-axis that's something we're trying to learn more about, something we're trying to figure out how it's responding to a change in the other variable which we're putting in the x-axis. So for example, we very often would put something like time on the x-axis. We're not looking at how other things affect time. Time rolls on no matter what we do. But we put time on the x-axis and look at how things are changing over time. So very often right now, if you look in news articles, you'll see charts about number of people infected with COVID-19, for example, and we'd see how that's changing over time. So again, we put time in the x-axis, we put something else on the y-axis that we're interested in learning more about, and we look at that relationship. Now, when we're looking at data in a scatter plot, very often, as we've seen, dots are kind of scattered all over the place. And so a really powerful tool for helping us figure out the relationship between these two variables is to simplify that relationship by fitting a line to it. So we've talked about describing whether the relationship appears to be linear or not. And if it is linear, we can fit a line to the data. There's some math behind how to figure out where exactly that line should be, and we kind of brush along the surface of that, but we don't get into the weeds of it. The important thing for us to know is that basically with some math equations, we can figure out the best place to put a line to describe that relationship. And what it's going to do is we're going to not be able to go through every dot on that scatter plot when we're fitting a line to something. We're going to kind of put a line in the middle. Makes sense, right? And so there's going to be a difference between where the line is and where a lot of the dots are. What the math does is it looks at that difference between where the dot is and where the line goes, and it makes that difference as small as possible. So we call it a least squares line. That's the most commonly used equation to figure out where the best line should be. That's the one that is the standard in the literature in most research areas. That's what we're going to be talking about. It's often called ordinary least squares, or OLS. So that is what we talk about when we talk about a regression and fitting a line. And next week we'll get into why it's so powerful and how we can use it in so many different applications. But for this week we're gonna be thinking about fitting a line to data to describe a relationship, what that means, and to some extent, how can we get a sense of whether it's doing a good job or not. So the first thing we want to do, as we've already talked about, when we have a scatter plot, we look at a direction, we look at form, whether it's linear or not, and we look at strength of a relationship. Well, that middle one, the form, whether it's linear or not, is an important thing to think about, because if we're using a line to describe a relationship, but it's a nonlinear relationship, it makes sense that a line's not going to do a good job at all. So we want to make sure we're dealing with a relationship that's at least somewhat linear when we're fitting a line to data. We want to make sure that we are talking about quantitative variables, at least as we start here. We need to be wary of outliers. So outliers can really drive where a line is going to go. If you think about the best line to describe a relationship, but we've got some outliers, well, the line's trying to include those, which means those outliers can have a big effect on where the line is going to go when we're trying to describe a relationship. So this is one of those situations where often what we'll want to do is figure out where a line should go, both with outliers and without outliers. If we exclude the outliers, where would the line go? And present both of those pieces of information, both with and without outliers, and the decision maker who's trying to do something based on this data, they can decide for their application, does it make sense to use one line or another line? With outliers, without outliers. There's one other thing we're going to look for with a linear regression, and it's something called the equal spread condition. We want to make sure that that is met. The equal spread condition is saying that the relationship isn't fundamentally changing as we go from small values to large values along the x-axis. As we go from left to right along the scatter plot, is the relationship changing in an important way? And what the equal spread condition is really saying is, do things get further away, more scattered from where the line will be as we move from left to right? So then it would be kind of fanning out to the right. Or are they more spread out as we're at small values of x and they get closer and closer to where the line is as we go to larger values? That would be fanning out to the left. Or is it roughly spread out in an equal way as we go across? And we would call that equal spread. Ideally, that's what we're looking for, is that the spread doesn't change a lot as we're going from small to high values. It's something that we actually have statistical tools to deal with, that if you go on to advanced statistics courses, they'll talk about heteroscedasticity and heteroscedastic robust standard errors, really fancy words. For us, we want to just be able to recognize if a relationship seems to be changing in a big way, with the residuals fanning out to either the left or right, then we'll say there may be a problem with the equal spread condition. We'll be talking more about residuals and kind of what that means for checking the line in a little bit. So this is kind of our first little video about linear regression. We'll be posting the next one about residuals, and then there will be a third one about R squared as a measure of linear fit. I'll see you soon.